Hey everyone, in this video we are going to discuss about recursive least squares, that is RLS adaptive filter. So we will see first what is meant by RLS algorithm, and we will apply this algorithm for a particular type of signal. Then we will see the output, how we are getting the adaptive filtered output. So before going to this concept, actually first we will discuss why we should use adaptive filters. So we know in digital communication, so when we transmit a signal through the environment, at that moment noise will be added to the actual signal which we have transmitted. So it will create a problem at the receiving end. So we will be transmitting the signal and we will be receiving the signal. So in between there will be a problem due to the noise. So in order to remove that noise, we are using the filters. So we can't use the static filters, because so basically filter is nothing but a matrix which consists of some coefficients, and that matrix is multiplied with the incoming signal in order to cancel some part of the incoming signal, that is basically the noise part. So once that noise part is removed, the signal which is remaining will be the actual signal which we have transmitted. So that's the ultimate aim of filtering, where we are removing the noise. So how the static filter cannot be used, because the input signal is not constant. So the environment is changing, the signal itself is changing, so the fixed coefficient of the matrix are not suitable. So as the signal changes, the coefficient of the multiplying matrix should change. So the filter should not be static, it should be adaptive. So it should adapt with the incoming signal. So that's why we'll go for the adaptive filters here. So this concept, I hope you understood that what is meant by filter and why we should go for adaptive filter rather than the static filter here. All right, so coming to the recursive least square RLS algorithm. So before this we have one more algorithm, that is least square mean algorithm, LMS algorithm that is called. And that algorithm is used for creating the adaptive filter as well. But the problem with that algorithm was that we have to decide the step size there, that is denoted by mu. So that is this one, mu. So there we have to predict the value of mu, but which is very typical when the input signal is having lot of noise. At that time the prediction of mu becomes very tougher. So don't want to predict the mu, so we just want to take the present input, and we will use some our previous experience to derive the coefficients for the present input signal. So that is basically done in the RLS instead of LMS. So I can say RLS is the continued part for the LMS algorithm. So basically we are developing the algorithm and we are giving to the adaptive filters here. So it may be LMS algorithm, RMS algorithm, or steepest descent algorithm. So anyone. So we are just using some algorithm to make our signal better. So that's the ultimate aim, where we want to remove the error or we want to minimize the error. So of course we can't remove the error. So there is no such thing like zero error signal. So it is only in books, but in practical life we don't have any signal which is having zero error. So every signal contains the error, but we just try to minimize that error. All right, so I will start with the drawbacks of LMS filter. So that will give a picture to you why we are going for the RLS algorithm actually. So the first problem was, though LMS algorithm is computationally simple, its convergence rate is low. So particularly when eigenvalues of the autocorrelation matrix RY are widely spread. So though the LMS algorithm was simple for implementation, the convergence rate, that is the rate at which the symbols are coming towards each other, so it was very low. So it should be high for a adaptive filter. So convergence means 2 points will be moving to each other. In this case, two values will be moving to each other. So that was low in case of LMS algorithm, particularly when eigenvalues of the autocorrelation matrix Ry are widely spread, means they are having a large difference in between them. So that means lambda max by lambda minimum will be greater than 1, because the lambda maximum and lambda minimum are greater number. So there is a lot of difference between these two values. So at that time the output will be greater than 1. Okay, so that's the first reason why we are going for the RLS, or we can say drawback of the LMS algorithm. And coming to the second, step size parameter is to be properly chosen. So in case of LMS algorithm, we have to predict the step size properly. Otherwise, the LMS algorithm will going to fail. So it will give a saturated estimation or the parameters filter coefficient. Okay, so the excess mean square error is high due to the longer step size. So here this clarifies the second point here. So if we predict mu value greater than what it is needed, at that time the problem of excess mean square error happens, where the output will be having excess mean rather than the expected value there. Okay, so and coming to the why we should go for RLS algorithm. So there are few points here. The RLS algorithm converges faster even when the eigenvalue spread of the autocorrelation matrix is large. So even though the eigenvalue spread of the autocorrelation matrix is large, that is basically I can say the first point which is mentioned in LMS is solved by the RLS algorithm. And the problem of selecting a proper step size parameter, that is mu, is avoided here. So they in case of RLS algorithm, there is no need to select the step size mu. So we don't have any step of selecting like this. Okay, so but only drawback for the RLS algorithm is higher computational complexity. So what makes it higher, most complicated is the taking inverse of the coefficient. So we will be having the output relation, so we need to take its inverse in order to find out the filter coefficient. So that is the complexity which is involved, but of course it can be overcome with the help of some particular type of special algorithm, so that I have discussed in upcoming session. Okay, all right, so this is the diagram for adaptive FIR filter. So FIR means finite order filter, that is it is having only the present value, and past values are discarded here. So all right, so it contains of the input signal y of n, that is the signal which is traveled through the environment, and it contains the noise here. So it is passed through the adaptive filter, and then we are getting the estimate of the expected signal. So here we will be having a expected signal denoted by d of n, and the signal which is coming from the adaptive filter here, that is d hat of n. So the actual signal, that is desired signal, and the output signal, both are compared, or you can say the difference is taken between the actual signal and the output signal. So that will basically give me the error. So that error signal is given to the adaptive algorithm. So here RLS algorithm plays the role. So I can say RLS algorithm is sitting here, and that is helping the adaptive filter to make the related corrections to the coefficients of the filter here. So it is basically updating the coefficient matrix of the adaptive filter. So RLS algorithm play the role in the adaptive algorithm section. Okay, so that will basically change the adaptive filter coefficient. So now you have got the idea where the RLS algorithm is sitting and what it is doing. So now the LMS algorithm minimizes the instantaneous square error E square of n. So this is instantaneous square error, and where E of n is denoted by, so this we have got from the LMS algorithm derivation. So if you have not seen that video, please check the playlist so you can find the LMS video as well. So E of n will be equal to x of n minus h inverse of n into yn. So where y of n is the input signal, that is this one, that is we have received from the environment, that contains the noise, and h inverse of n is the filter coefficient, that is I can say the response of the adaptive filter. So which I can write it as x of n minus y dash of n into h of n. So this can be written like this with the help of the matrix properties. So the RLS approach minimizes the sum square error between the desired signal d of n and the filtered output d cap of n or d hat of n. So basically RLS algorithm tries to minimize the sum square error, that is E of n error, so which is the difference of the desired signal and the output signal. So the RLS algorithm considers all the available data up to the current time for finding the filter parameters. So what are all the available data are present up to the present time, at which instant we are trying to find out the error, at that until that moment all the parameters are considered in case of the RLS algorithm. So the estimation problem is solved recursively, that is repeatedly. So least square estimation problem is solved recursively means we are following the same steps again and again. So that's why it is called recursive least square algorithm. Alright, so now we will try to find out the weighted sum square error for the RLS adaptive filter. So basically we want to minimize this sum square error, that we can call it as SSE. So that is written as weighted because it will be the summation of the present output and the previous output is also taken, so in order to make the filter adaptive. Alright, so that will be the basic addition of the previous and the present input, so that's why it is called as weighted. Okay, so first we have h of n equal to, so this is a vector which consists of coefficients h naught n, h1 n and up to hm minus n. So is the filter coefficient vector at instant n. So this is the filter coefficient vector. So basically this forms the adaptive filter here, and these are the components of the vector which are involved in the filter construction. Okay, so here the cost function of the RLS adaptive filter is the weighted SSE, that is sum square error given by. So the cost function means nothing but the sum square error. So the cost function and SSE both are same. So we just want to reduce the cost function, or we want to reduce the sum square error, that is given as E of n here. So E of n equal to k equal to 0 to n lambda to the power n minus k into E square of k. So this is the error which is that is sum square error. So and when we take a summation, that is k equal to 0 to n and lambda to the power n minus k, so E square k we have seen previously, it can be written as expected signal d of k minus this is the filter expression y dash of k into h of n. So this is the input which is coming to the filter, and this is the filter property. So it is something like this. So we have got a filter here. So its property is h of n, or the transfer function, and we are getting y of k here, and we are comparing it with the d of k, that is the expected signal over here. Alright, so then we will be taking a feedback, then giving it to the algorithm, that is RLS algorithm, then that will change this filter. So it is basically an adaptive filter, so I can mark it like this. So it will be taking the input from this as well. Alright, so I can write E square of k like this also. So then k equal to 0 n lambda to the power n minus k d of k minus due to the properties of vectors I can shift the inverse to the other one. So h inverse of n into yk, so I can write like this. So where ek is the filtering error at instant k, so this is the filtering error due to the h of n. So due to h of n, what will be the filtering error at that k instant is found. So lambda is called the forgetting factor whose value is between 0 and 1. So here lambda will be the forgetting factor, so whose value is typically between 0 and 1. So if it exceeds the 1, then it is called as oversaturation. Alright, so previously we have seen the importance of lambda. Now we will see. So previously we have seen that the lambda value is between 0 and 1. So why it should be 0 between 0 and 1, we will see now. So past filtering errors E of k, that is k is from 0 to n, are computed with the most recent filter h of n. So the past filtering errors, that is the previous filtering errors, are found with the help of present uh, most recent filter, that is h of n. So the filter will be continuously updating, so the past errors are found with the help of the present filter coefficients here. So recent error is given more weightage and past errors are given smaller and smaller weightage. So as the filter is updating continuously, the previous, that is the old errors are given more weightage than the so the old that is the I can say recent errors are given more weightage. So what are the present errors, so it will try to reduce that one rather than reducing the past errors here. So the weightage will be more for the present errors, and it will be less for the past errors here. So due to this property, this allows the filter coefficients to adapt to the non-stationary in data. So non-stationary data means the data will be continuously changing. So the filter is able to adapt to the non-stationary means as the data changes, the filter is going to update itself, or it will update its coefficient according to that one. So that is the most important property an adaptive filter should have. So it should be able to adapt itself as the incoming data changes. So that is satisfied by the RLS algorithm here. So for stationary case, lambda should be equal to 1. Then for if the data is stationary, then we can take lambda equal to 1 directly. Alright, so now we will see how to minimize the error here. So actual derivation will be the minimization of this error, so that we can call it as the supportive document for this one. Okay, so to find or to minimize the error, epsilon n, that is the error, is equal to k equal to 0 to n. So we have previously seen this equation. So what I will do, I will differentiate this equation with h of n, that is filter response, and equate it to 0. So if this differentiation, so differentiation means change in the input. So if this change in the input is 0, then we can say the input signal is same as the transmit received signal is same as the transmitted signal. So that's why in every case we'll be taking differentiation. So basically the differentiation of a constant line will be equal to 0, and for differentiation of a line which is like this, will be having some value greater than 1. So differentiation tells the change in the input. So if this differentiation of the error signal will be equal to 0, at that time it indicates no error is present. Okay, so that's why we are taking differentiation and equating it to the 0 here. Okay, so let us take differentiation, then x to the power x square form it will be taking. So we know those basic formulas. Then 2 I will take outside, then lambda to the power n minus k dk minus y dash of k into h of n. Inner differentiation for this one will be y of k, as it is with respect to the h of n here. So 2 I can take again outside, and dk yk, so multiply inside the bracket, then we will get this equation. So I can write like this. So k equal to 0 to n. So when I will take this side, the 2 will get cancelled, that is with the 0. So I will be left with k equal to 0 to lambda to the power n minus k yk into y dash of k. So I am segregating the yk and y dash of, so that I can get h of n here, and then a summation k equal to 0 to n lambda to the power n minus k dk into yk. So this I can name it as second equation. So this is called the normal equation for LS estimation. Alright, so I have taken from equation 2, that is from this one, I will take it as ry hat of n, and this I will take it as small rdy hat of n. So that I have written here. So from equation 2, I will take ry hat of n equal to summation k equal to 0 to n lambda to the power n minus k yk into y dash of k. So that is the estimator for autocorrelation matrix ry. So as you can see here, the coefficients are same, that is the input signal is in the inverse form. So this is yk and y dash of k. So autocorrelation means same types of coefficients are present, and cross correlation means two different types of coefficients are multiplied together. At that time we will call it as cross correlation, because two types of coefficients are present there. So similarly I will write I'm just assuming this one, so it is bulkier to write, so that's why I'm taking in the smaller form. So small r dy hat of n is equal to k equal to 0 to n lambda to the power n minus k dk into yk. So I'm taking this one. So basically this equation I'm taking it as small r dy hat of n. All right, so that is estimator for correlation vector. So as I've said, this contains yk and dk. So this is the desired signal and this is the input signal. So these do not belong to the same family. So it is called as cross correlation, as it is between two different types of inputs here. Alright, so equation 2 becomes, so I can write equation 2 as ry hat of n into hn equal to r dy hat of n. So from this I can write hn equal to ry hat of inverse. So this will come in the denominator, then when we take it to the numerator it will be inverse form. So r dy hat of n. So this is the solution to the normal equation. So but the problem with this one is that how I can take the inverse here. So it is very complex. So as I said earlier, in RLS algorithm, the very complex step is to take the inverse of the coefficients here. So how I can take, we will see. So but in the above equation, matrix inversion is involved, which is computationally complex for the direct solution. So we'll go for the recursive solution. So directly taking inverse is very complex. So we'll go for the recursive solution here. Okay, so recursive representation of r hat of ry hat of n. So how I can recursively represent this ry hat of n? Okay, so ry hat of n equal to, we know this relation. So as we have just seen, so y of n into y dash of n I can write. Okay, so once I will take lambda. So here we can say from this equation I am writing like this, but the question arises how I can write like this. Okay, so as you can see I have changed the limit here from k is equal to 0 to n. I have changed it to k equal to 0 to n minus 1. So as you can see, up to when k is equal to k, when I put k equal to n here, so at that time this will become 0 and we will be left with only y of n into y dash of n. So this component is for, so it is something like this. We are running from 0 up to n, we have a value, and this is a n minus 1. We are taking this part. Okay, so this part is the, this part here. So and the addition is the second part which is present. So it will come only when we you put in this equation k equal to n. So when you put k equal to n, lambda to the power n minus n, it will be equal to 0 and 1. So this will this whole term will go here and we will be left only with okay, so this term will go, we will be left with you can see here, so we will be left with only y of n into y dash of n. So I have written y of n into y dash of n. Alright, so I hope you understood why I'm writing. When I change the limit by 1, then I will be having this extra term here. Okay, so I will take lambda outside and multiply with lambda to the power n minus 1 minus k. So when I take inside, this plus 1 and this minus 1 cancel and I will be left with only lambda to the power n minus k. And the rest things are same, y of k into y dash of k plus y of n into y dash of n. So I can write it as lambda into, so this is the representation for ry hat of n minus 1. Okay, so there is n minus 1 involved here, so I will represent like this. Then I will go for the second part, that is y of n into y dash of n. So I can write ry hat of n equal to lambda into ry hat of n minus 1 plus y of n into y dash of n. So this is the recursive. So the above equation shows that autocorrelation matrix can be recursively computed from its previous values and the present data vector. So you can see the autocorrelation matrix, that is RY hat of n, can be created by previous values, that is RY hat of n minus 1. So this is the previous value and these are the present values, y of n and y dash of n. So lambda is the forgetting factor, that is basically a scaling factor there. So as so these this equation tells basically it can be computed from its previous values and the present data vector. So this is the data vector, 1 cross 1 vector will be there and 1 cross 1 vector will be there. So this is the vector and this is the previous data vector. Okay, so similarly I can write for the cross correlation as well. So I will follow the same steps, so I have not done, so directly we will be getting this equation right there. So r dy hat of n will be equal to lambda into 2 r dy hat of n minus 1 plus d of n into y of n. Okay, so here we have a previous value and the desired signal. So this is the cross correlation because there are two different types of signals multiplied. Okay, so recursive solution of the normal equation. So we have got the normal equation. So how I can take the recursive solution for that one, we will see now. So we know that from equation A. So we have previously the equation A. From that h of n I can write it as ry hat of n to the power inverse r dy hat of n here. So I can write like this. So r y hat of n I have find out. So that is from equation 3 I will put this one and to the inverse r dy hat of n. So above equation shows some matrix is obtained by adding a rank 1 part at each instant. So this is the sum matrix. So this is the rank 1 part here, y of n into y dash of n, that is 1 cross 1 matrix, and it is added to the some previous matrix. So that is we are getting the sum matrix here by adding these two components. Okay, so how I can take the matrix inversion, that is ry hat of n inverse. So that is with the help of matrix inversion lemma. So if that's just an example how we can take. So if A is an m cross m non-singular matrix, then u and v are the two column vectors. So at that moment how I can take the inverse for this whole thing, a plus uv a dash in to the power inverse. So I have a direct formula for this one. So if you know a inverse minus, then you can take the whole inverse for this one. So it will just reduce our complexity. So a inverse minus a inverse into uv dash a inverse divided by 1 plus v dash into a inverse u. So where the denominator should not be equal to 0, then if it equal to 0, then the whole thing will go to the infinity. So it should not be equal to 0. So this is known as Sherman Morrison formula. Here if you know a inverse, the inverse of the rank 1 increment, that is a plus cv dash inverse, can be found. So if you know just a inverse in this case, then you can take the inverse of this whole thing. As you can see, only a inverse is involved here, other things are there in normal form itself. Alright, so now we will see how I can take the inverse, that is ry hat inverse of n. So we have seen the Sherman Morrison formula to take the inverse of a rank 1 non-singular matrix. So now we will apply the same thing, that is same formula for this one to take the inverse here. So we know this relation, we have just seen that one. So let us take a equal to lambda into ry hat of n minus 1 and uv equal to yn. So you can just recall this one. It is taken from the equation 3 here. So let me just show you. So it is taken from the equation 3. Yeah, as you can see, a is this one and u is this one and v is this one as well. So they are in the inverse formula itself, inverse form. Okay, so a is this one, u and v. So I have to take the inverse of this one, ry hat of n inverse. So that's why I have taken a and ev here. Okay, so let me just show you how I can take. Okay, so applying this formula, we will be getting ry hat of inverse of n equal to lambda into ry hat of n minus 1. So a inverse I am taking. So plus yn into yn hat into yn dash of inverse. So I have taken in this form. Then apply this formula. So I will be getting a inverse. So a inverse means 1 divided by lambda ry hat of inverse n minus 1 minus a inverse again. So write the same thing here. Then uv dash. So u is this one and v is this one. A dash is there, so I will put a dash. Then a inverse again multiply with this factor. So 1 plus v dash and a inverse again write it here. Then multiply it with y of n. So I have put in this equation all the terms here. Then simplify. 1 by lambda you take outside, ry hat of inverse n minus 1 minus 1 by lambda is taken outside, we will be left with ry hat inverse of n minus 1 y of n and y dash of n ry hat of inverse n minus 1. So here we have to take the LCM first. So lambda will be multiplied to the 1 and the denominator lambda will be taken outside. So we'll be getting lambda plus y dash of n, and this term has gone, ry hat of inverse n minus 1 into y of n. So that is fifth equation. So let us assume Just to make it simplify or simpler for calculating, I will be taking p of n equal to ry hat inverse of n. So I am denoting this term as the p of n here. So I will be getting p of n equal to 1 by lambda p of n minus 1. So this I can write p of n minus 1, and similar changes are made here. So p of n equal to 1 by lambda outside, p of n minus 1. So this term I am taking it as k of n here. So what are all included in this one is the, this whole thing is taken as the k of n, which is called as gain vector. So I am denoting it with the help of k of n, and the rest things y dash of n and p of n minus 1 I have written as it is. So we'll get equation 6. Then where k of n is called as gain vector, so k of n will be equal to p of n minus 1 into y of n divided by lambda plus y dash of n into p of n minus 1 y of n. Okay, so from this one I can write, take the cross multiplication lambda into k of n, and these transfer these terms to the left hand side. So we'll be getting k of n into y dash of n, then p of n minus n into y of n, and this one I am taking to the right hand side. I will be getting minus p of n minus 1 into y of n. So this result we will be using in future derivations. Okay, so now we'll see something more about the gain vector k of n. So it is important for interpreting adaptation. So k of n is very important for interpreting the adaptation, and it is related to the current data vector y of n by relation. So it is related to the current vector, that is y of n input by the relation. K of n will be equal to the multiplication of p of n and the y of n. So to prove the above relation, so to show it is actually related, so let me just derive a derivation here. So I know p of n equal to 1 by lambda p of n minus 1 in minus k of n into y dash of n p of n minus 1. So you need not to do this in the exam, so I'm just doing it for the sake of understanding. Okay, so multiplied by, pre-multiplied by lambda and post multiply by y of n here for the above equation. So I'll be getting y lambda into p of n y of n, which is equal to, so I have multiplied with lambda, so the lambda will 1 by lambda into lambda will get cancelled. So I'll be left with p of n minus 1 minus k of n into y dash of n. So p of n minus 1, again I'm multiplying by y of n, so whole multiplied by y of n. So you just take it out inside, p of n minus 1 into y of n minus k of n into y dash of n into p of n minus 1 into y of n. So this we have previously seen. This is the relation for, or expression for, lambda into k of n. So I will replace it with the lambda into k of n here. So that's why I can write, so lambda into k of n is here, and lambda into p of n into y of n is here. So lambda will get cancelled. K of n will be equal to the multiplication of p of n and y of n here. So hence we have proved the above relation. Okay, so now we have found the significance of the gain vector. So the last step is to how to get the filter updates here. So as we have said, the filter is getting updated itself. So how it will update itself, we will see. So h of n equal to ry hat of n inverse into r dy hat of n. So this relation we know. So I can write this one as the p of n into lambda into r dy hat of n minus 1 plus d of n into y of n. So this I can replace with the this relation, and lambda I will take outside, p of n into multiplication I will solve here. So lambda into, so p of n you just substitute for p of n again here. So p of n is represented by 1 by lambda into p of n minus 1 minus k of n into y dash of n p n minus 1. So this term you write as it is, r dy hat of n minus 1 plus d of n into p of n into y of n. Okay, so this multiplication gives the filter coefficient here, r dy hat of n minus 1 and pn minus 1. So this is giving the filter coefficient h of n minus 1 minus k of n into, so this will get cancelled, and p of n minus 1 into r dy hat of n minus will give the filter coefficient h of n minus 1, and k of n as it is y dash of n, and again p of n minus 1 r dy hat of n minus 1, this will give the h of n minus 1, that is filter response, plus d of n into k of n here. Okay, so h of n minus 1 plus k of n. So I'm just rewriting this one. K of n I'm taken this side, and d of n in d of n minus y dash of n into h of n minus 1. Just I will rewrite it here, and then I can write the final equation like this. So h of n minus 1 plus k of n into d of n minus y dash of n into h of n minus 1. So as you can see, this is the previous result, that is the previous filter, previous vector or the previous filter output, and factor of multiplication, that is gain vector k of n, and this is the error. So this is the desired signal d of n, and this is the input signal y dash of n, and this is the filter response, that is the previous filter response. So that's why you can say RLS algorithm uses the previous or the past experience to calculate the present values. So you can see clearly from the equation n minus 1 is involved, so it is using the previous values to calculate the present error. So to reduce the present error, it is using the previous values. Alright, so till now we have seen how the RLS algorithm works, and what are all the importance of lambda, k of n, what is meant by gain vector, and how the filter coefficients are updated, and how it can be recovered from the previous values, that is the previous outputs of the filter. So we will quickly see the overall steps which are needed for the RLS algorithm. So first, initialization, p of minus 1 should be equal to 1 by delta into 1 of m cross m, so where delta a small positive number. So here delta is a small number, so that it will be merely one m cross m identity matrix here. So as we can see, as the delta value decreases, 1 by delta will go to the higher value. So this is the identity matrix I of m cross m. So if this value increases, then the diagonal elements in the identity matrix will increase. So it will be something like this. We have identity matrix, that is 1010, and here 1 by delta is there. So if its value increases, so let us say 5 it will be, then these two become 5. If it is 6, then these two become 6. So if the 1 by delta value increases, then the diagonal matrix will increase, so the chances of clear filtering will be increasing. So that in this relation we should take lambda as small as possible. So h of minus 1, that is the previous output, first we will be choosing it as 0, and choose a lambda also, that is suitable between 0 and 1. Okay, so coming to the operation steps. So operation consists of, for n equal to 0 to 1, first we need to get the d of n, that is desired signal and the received signal through the environment. Then compute the error e of n equal to d of n minus h dash of n minus 1 y of n, that is the previous output of the filter and desired signal and the present input. Then gain vector, find out the gain vector by this formula, then update the filter parameters by this formula, then update the a P matrix, that is with the help of this formula. So these are all the steps which are involved in the RLS algorithm, and I hope you understood how the adaptive filter works with the help of RLS algorithm, and you liked the content. So I hope you give the like and subscribe the channel for more updates. Thank you. Thanks for watching.